Alright, because this is ubiquitous in mathematics, we're going to go over a little bit of set theory. So here's a set theory and notation primer. So first of all, a set is just a collection of stuff. E.g., we'll call a set here X, and it's just this kind of squirrely bracket here, and it contains some numbers 1, 2, 3, 4, and another little squirrely bracket. That's one example of a set. Another example, we can call it S, and it can be filled with letters, say A, B, C, D. Now, a set doesn't count, or rather, it only counts unique elements, only counts unique items in the collection. So for instance, this set, A, B, C, D, is the same thing as this set, A, B, C, D. That is, just because there are 3 A's when we write it down, it represents the same abstract mathematical object that this set does, and we call them both, say, S. Another example of a set is all real numbers, so 1.235, or 3.141592653, or 2.17, or whatever. Those are all parts of the set of real numbers. Another example of a set might just be this T here, where it's just a collection of triangles. So a set isn't limited to numbers or symbols, but we usually just use numbers and symbols. Okay, so the empty set. So when a set doesn't have anything in it at all, we call it the empty set. And that's usually written down as something like this, or perhaps a phi, the Greek letter phi, or just this funny symbol. I didn't write it very well, so I'll write it again. It's kind of a 0 with like a cross through it. And that's the empty set. It means the same thing as just a pair of empty set brackets. And it just represents the set with nothing in it. Okay, so there are operations that we can do on sets to make new sets or to relate sets to other sets. The first one is called union. The union of one set with another is just the set that contains all of the elements that are in both of them, that is, all of them together. So the union of 1, 2, 3, 4 with 7, 8, 9 is 1, 2, 3, 4, 7, 8, 9, and that's the union. So if it's in the first set or the second set, then it's in the union. The next major operation, looks like I had another plan here. Right, the order of elements in a set doesn't matter, so ABC is the same thing as CAB. Those are both the same set. Order isn't important, just whether or not an element is in the set. Okay, the next major operation is intersection. So intersection of sets, if it is in one set and another set, that is, if it's in both of them, then it's in the intersection. So the intersection of 1, 2, 3, 4 with 2, 7, 3, 9 is 2 and 3, because 2 and 3 are in both sets, and they're not in, 2 and 3 are in both sets, and 1 is only in the first set, and 4 is only in the first set, and 7 is only in the second set, and 9 is only in the second set. So the intersection is everything that's in both. Okay, difference. Set difference is defined as anything that's in the first set that's not in the second set. So the difference between 1, 2, 3, 4, 5 and 2, 5, 4 is 1, 3, because 1, 3 is in the first set, but it's not in the second set. So it's like we're subtracting anything that's in this set from this set and writing it in the difference. So that's set difference. Subsets. Right, when everything in one set is in another set, then we say that the first set is a subset of the second one. So 1, 2 is a subset of 1, 3, 2, 5, because 1 and 2 are in this set, 1, 2. However, 1, 2, 3 is not a subset of 1, 2, 4, 5, because 3 is in the first set but not in the second set. So in order for one set to be a subset of the other, every element of the first has to be an element of the second. Okay, and there'll be more set theory coming up.